Hello. Hello. Oh, it's sucking. HMM. We've seen HMM, no, yesterday. What is in HMM and all those things. So you have hidden states, sequence of hidden states, sequence of observations. Fine, we'll begin from HMM. So in HMM you have all these things. I think I've discussed even this. I've even discussed this. I think I added this newly. In a Markov model, you do not have anything like observations or anything. It's only in hidden Markov model that you have separate set of states, hidden states, and a separate set of observables. So if you look at if you look at Markov model, you have a simple, you have something that looks like this. The probability of all the states, so state 0, state 1, and so on until state t, the probability of all of that is given by this initial probability into the product of all transition probabilities. In hidden Markov model, you go one step further because it's not just states now, hidden states, you also have observations. So the probability of state 0, state 1, state 2, so on and so forth, along with observation 0, observation 1, 2, 3, 4 till observation t, it is given by a probability of state 1 into product of all the transition probabilities and product of all the emission probabilities. And if you remember, transition probability is from state to state, and emission probability is what is the probability of an observation given we are at a certain state. So this is from 0 to t. If it's for a certain sequence, then this will change. For example, probability of S1, comma S2, what is that going to be, and so on and so forth. We'll look at some examples later. Yesterday I gave this as an example of a hidden Markov model. You have hidden states, and then you have the observables. You can observe whether your lab mate is wet or your lab mate is dry. So these are your observables. Emission probability, it will be of the size number of hidden states cross number of observables. So you have 3 hidden states. So you have a 3 cross 2 matrix. And this is the initial probability distribution. It is given that it is 1, but it need not be the case. It could also be like this one. Probability of S0 is 0.4, 0.3, 0.2, whatever. At last the sum should be 1. 4, 5, 6, 7, 8, 9. Okay, something else is missing. So here the probability distribution is like this. 1, 0, 0. Probability of Sunny is 1. Probability of S0 equal to Sunny is 1. The other probabilities are 0. Since S0 is a random variable, the probability of a random variable is a vector of probabilities. So the first one is nothing but the probability of S0 being sunny. Second one is probability of S0 being cloudy. Third one is a probability of S0 being rainy. You can change this, but in this question, probability of S0 being sunny is 1. Fine, we'll solve some questions. So let's say one question is like this. You are stuck in a lab for 3 days. So if you're stuck in a lab, you will not be able to know what is the weather outside. So the hidden Markov model is a good representation. You do not know what is the state of the weather, but all that you know is the state of your lab mate. Your lab mate is either dry or wet. So what happens is on day 1, or it begins with 0. So on day 0 you don't know what happened outside. It was either sunny, rainy, or cloudy, but your lab mate was dry. On day 1, after day 0, you do not know what was the weather outside, but you saw that your lab mate was wet. And on the other day, you do not know what was the weather. Again, this is hidden, so you will never be able to know what was happening outside. But your observation is that the lab mate was wet. So this is the observation sequence. If you realize, you have this, right? You have this representation of hidden Markov model. This will not change. This represents all the transition probabilities and emission probabilities. Here on the right side, if you can see this is, if you notice, this looks like a Bayes network, right? This is like a directed acyclic graph. This is not a Bayes network. This is a Bayes network. So what does this represent? It represents how does the world change as time passes. So the weather was initially at S0 state, then it went to S1 state, it went to S2 state. So this keeps changing. This moves on till time infinity. It goes on. So this is like a representation of how the states in a hidden Markov model change. Fine, the question is this one. So you have an observation sequence, dry, wet, wet. Now they're asking us to find the probability that it is raining outside now. So if you're stuck in the lab for 3 days, it means S0 is over, S1 is over. Now it is S2. You're in day 2. Day 0 is over, day 1 is over. Now you're in day 2. You are here. Now they're asking you to find the probability that it's raining outside. So how do you write it using symbols? You have to find the probability that S2 is equal to R. It means you have to find the probability that it is raining outside on day 2. But that's not the only thing that's been given, right? You have some extra information. On day 0, the observation is dry. On day 1, the observation is wet. On day 2, the observation is wet. So that is what I wrote here. So given this is the observation sequence, what is the probability that day 2 is raining? S2 is equal to R. So you can use your rules of probability. A probability of A given B is nothing but probability of A and B by probability of B. So this denominator is a constant. So what I'll do is I will represent it by, so 1 by denominator, I'm writing it as alpha, some constant. We'll come back to this constant later. So the main thing here is how do we calculate the numerator. See, in some cases, wherever you have a vector of probabilities, the alpha is a normalizing constant. But here there's no vector of probabilities. So this alpha is just like a constant. You need not call it a normalizing constant. So anyways, how do I find this one? So there is a nice formula that lets us know, or a formula that tells us the relationship between the probability of a certain state and some sequence of observations. It relates this with the probability of a previous state and the previous set of observations. So if you look at this, you can try to make sense of this. So probability of a certain state, see, nothing is assigned to ST, so it's a random variable. All the other observation variables have some values, so they're not random variables, they're propositions. So the probability of this random variable along with all these observations is given by this one. So this is the probability of ST minus 1 equal to I. So it means in the previous state you were at state I, and the observations here you're taking from O0 to OT minus 1. Here capital O is the random variable and small o is the value. We looked at probabilities yesterday, no? Capital letter means random variable, small letter means it's a value, it's a proposition. So this multiplied by the transition. So it's like you are at state I, and then you're transitioning from state I to state ST. And along with that, you're also multiplying with the emission probability, because at state Si, after you transitioned from state I, you're observing observation OT. So you'll be observing OT given you're at state ST. So this is just a formula. So we'll be using this formula. So we'll be splitting this one. So if we split this thing using this formula, we will get something in terms of probability of S1. Right? So first what we'll do is, we'll first find what is the probability of S1. So probability of S1 given the sequence of observations until that given day. So this state is ST minus 1, right? Here the observations also end at T minus 1. So first we'll try to find what is this. Mind you, this is a random variable S1. So I did not assign sunny, cloudy or rainy yet. So I'll get a vector of probabilities. So probability of S1 along with these observations, I can apply my formula here, this formula. Where is it? Okay, instead of calling this one, I'll call this the HMM formula, the main HMM formula. So you can apply your HMM formula here, right? Or you could, okay, fine, just apply this formula. This also works. So this will be summation. If you write this in terms of this, you'll get summation of probability of S1, and then you're coming from S0, right? Equal to I, probability of S1, no, T minus 1, right? So 1 minus 1 is 0, equal to I, and then the observation at O0 is D. T minus 1, so this ends here, and then probability of O1. What is the observation at O1? W, given ST. ST is S1. So this is the formula. But then if you realize probability of S0 equal to S is 1, and probability of S0 equal to C, or probability of S0 equal to R is 0. So the summation will finally just be this one. You'll only have S0 equal to S, all the other values will be 0. You can try opening the summation. You'll realize that S0 equal to S will only remain here. Only because the initial probability distribution said that probability of S0 equal to S is 1. If there was some other probability distribution, then you would have found some form of summation here. Now after I get this, I'm supposed to simplify this. So let us open this term. How do I open this term? Again, I think you can use this formula, no? Or if you use the main HMM formula, that will also work here. So I can write this as probability of S0 equal to S, or fine, you can use this this one here. Probability of A and B is nothing but probability of A given B into probability of B. So I can use this rule and open this one, right? So here A is this one, B is this one. So A given B. So after I open, what I'm getting is this is already there in the emission probability. The current state is S and the observation is dry. So if you look at sunny state and dry, you will see this one. Sunny state and dry is 0.9. So this emission probability is 0.9. And then probability of S not equal to S is 1. That's what I've been telling. The other terms in the summation will become 0 for this exact same reason. So finally what do you have? You have this one multiplied with 0.9 multiplied with this one. Now what I'll do is, we all know S1 is a random variable. So if I want to write the probability of a random variable, I'll have to write all possible values. So S1 can either be sunny, cloudy or rainy. I'm following this order that is given in the question: sunny, cloudy and rainy. So in the vector, the first element will have S1 as sunny, the second element will have S1 as cloudy, and the third element will have S1 as rainy. Now if you notice, these are just transition probabilities and these are just emission probabilities, and you have 0.9. So after doing all the math, you'll get some vector of probabilities. So this is the probability distribution of this one. So if S1 is sunny, you'll get this one. If S1 is rainy, you'll get cloudy, you'll get this one. If S1 is rainy, you'll get this one. But this was just a sub problem. The original problem is we have to find this one. Now it will be easier because when we open this using this formula, we have already pre-computed this value, so it will be easier for us to substitute. So let us see. This was our problem, right? So when you use that green color formula and write this one, you will realize that we have already computed this part. If you expand the summation, you will get this one. And this is a constant here. This is independent of x. The summation is over x, right? So this can come outside. This can come outside the summation. And the only thing that's getting summed is this one, this product. So x will be S, C and R. So you have to sum up all of this. We have already computed this in the form of a vector. So just pick those values. So 0.054, 0.081, all those will come here. And these are just transition probabilities. Look at the table and then you can substitute. Finally you'll get your probability. But this is just a numerator. This is just a numerator. We have something in the denominator, right? We had this one. So probability of this sequence of observations. So probability of this sequence of observations. How do we find this one? So you're supposed to find it this way. Since you have these since you have this sequence of observations, these observations can only arise if we've passed through certain states, right? If you look at this Bayesian network, these observations will arise only if some form of see, if you pass through these states only, you'll get these observations. It means you have to look at every possible sequence of hidden states that could have given rise to this particular sequence of observations. Yes. So that is what I wrote here. You have to cover all possible sequences of hidden states that could have possibly generated this observation sequence. A simple way to do that is start with introduce one hidden state and take the summation. Generally, you could have expanded it this way. You could have written summation. You could have expanded this as summation probability of S2 equal to some x, probability of S1 equal to some y. We already know that S0 is always S because probability of S0 is S, and then O0 is D, O1 is W, O2 is W. So, and summation is over X and Y. You could have directly written this, but what we'll do is we'll go step by step. Instead of introducing S1 here itself, let us simply introduce S2. See, what I'm trying to do here is introducing all the variables concerned from the Bayesian network. So if you have O0, O1, O2, it means you should have S0, S1, S2 as well. But as a first step, I will simply introduce S2, and I look at all possible combinations that S2 could take. So S2 could be sunny, cloudy, or rainy. If I open the summation, it will look like this. And if you realize, we just computed this one, the numerator, right? We got 0.04104. So similarly, you could compute this one and add it all up so that you get your denominator. So finally, this one divided by that denominator will be your probability. That was the first question. I think later on there'll be I think there are some algorithms that would simplify our process, but those algorithms are based on this probability only. Those algorithms will come at the very end. This forward algorithm and Viterbi algorithm, they solve two specific forms of questions within HMM. Second question, you're stuck in the lab for 3 days. You have the same observation sequence. Now they're asking you to find the probability that it will rain 2 days from now. So if you're stuck in the lab for 2 days, 3 days, so you'll be here, no? Day 1, day 2, day 3. Or day 0, day 1, day 2 is your third day. You're here. Now they're asking you to find the probability that it will rain 2 days from now. So 2 days from now means S4. So they're asking you to find the probability that S4 is raining. S4 is rain. But we know that this is given, right? So it is actually probability that S4 is raining, given that this is the observation sequence. But we know, if we looked at the previous problem, no, we know that finally it will boil down to this one only. This will be the numerator. If you look at this problem, it will all boil down to alpha times the numerator. So the numerator will simply be the hidden state and all the observations in the observation sequence. This given will become and then you simply have to multiply with alpha. How do you find the value of alpha? You can see, using the rules of probability, you will know what that alpha is. So we want to find probability of S4 equal to R given this is the sequence of observations. So after some simplification, what you'll get is you'll get some alpha times this numerator. So I will simply solve this numerator part because we've seen the alpha calculation and all. So here we can apply the green color formula, this green color formula. So we will be splitting this probability, right? So how does the green formula work? Since you have S4 equal to R, so you'll have to introduce S3 somewhere. So you'll be transitioning from S3 to S4. But since S3 is not mentioned originally, S3 could take any value. So S3 could be sunny, cloudy, or rainy. And that is why summation is there. This is transition. And then you have to find the probability of S3 and all the observations until day 3. But then observations are only until day 2. Day 0, day 1, day 2 observations are only there. So there is no emission because O4 is not there. You only have until O2. So nothing is here, so you just have to continue now. Now you have to split this as well. you have to split this. You have S3, so you use the green color formula and split it in such a way that now S2 is involved. So S3 is there. So S3, how will you split it? Now you'll get S3 given S2. So this is the transition probability. And now there'll be a probability in terms of S2. S2 given all the observations until that day. So O0, O1, O2 are observations until day 2. And there is no O3, so there is no emission probability on the right side. So this is there. And if you realize, we already computed something that looks like this. We have computed this one. Probability that S2 is raining along with this observation sequence. So similarly for other values of y, for example, cloudy, sunny, you should be able to follow the same process and be able to compute this one. And then you'll have to sum all of that. And then you'll have to do all of this to get the final probability. And that is still the numerator. There'll be some alpha here. You'll have to find what that alpha is. You'll get that alpha if you... So alpha is essentially 1 by probability of this observation sequence in this case, right? Right, because probability of A given B is nothing but probability of A and B divided by probability of B. So your B is this one. So your alpha is nothing but probability of this sequence, which you would have already computed here, no? We have already computed that probability here. So you just have to divide it with that probability. So these are two questions. So the first question was predicting the probability at that time. At time t, you have observations until time t and you want to predict what is happening outside at time t. The second question was you had observations until time t, but you had to predict something that happened after time t, that could possibly happen after time t. The next question is, okay, this was the question, no? So the next question is, you have observations, so you've been stuck in the lab for 4 days. So day 0, day 1, day 2, day 3, 4 days. So you are here, day 3. So they're asking you to find the probability that it was raining 2 days ago. So you have observations from day 0 to day 3. Now they're asking you to find the probability that it was raining at day 1. So if you write in terms of, if you represent this problem in terms of probability, you'll get this one. Probability that S1 is raining given this sequence of observations. The sequence of observation is O0 is dry, O1 is wet, O2 is wet, and O3 is dry. This is the sequence of observations. Now you can apply your this one. Is similar to Bayes' theorem, but not exactly Bayes' theorem. I forgot what this is called, but this is what we used previously, right? I think product rule, I don't remember the name, but this is the rule in probability. Probability of A. So probability, you know this rule. Now the new rule is that you have a C in the middle. I've already introduced these rules before. I think I can show it to you. No, it is somewhere far away. So I'll be using these rules to simplify this one. So consider this as A, this as C, this as B. So if I apply the formula, I will get this one. Feel free to pause the video if it is getting fast or whatever, or feel free to use 2x if you think it's getting slow. So now we'll look at the numerator and denominator separately. In the numerator we have, see, why are we splitting it this way? If you realize, we have kept we are trying to find the probability that S1 equal to R, right? So we have kept all the observations until S1 in the given side, and all the other relatively future observations for S1 along with S1. So this is what we are planning to do. We'll see how is it going to help. So I can rewrite the numerator as this one. For the numerator, I'll be applying this second rule. Probability of a comma b given c is equal to probability of uh, a given c. So I'm using this rule here. By this rule, I'll be able to write this one. So this is your A. I've highlighted the colors so that you understand those are the things that have been grouped as A, B, C or whatever. So in this case, this was A, this was B, and is that how it is? A, B, C. In this case, this is A, B, C. So you have A given C, you have B given A and C. Yes, so the formula is 2. Now we'll simplify this numerator. We know how to compute this, that is there. You have observation sequences from day 0 to day 1, and they're asking you to find the probability that at day 1 it was raining. So we know how to do this. The first question, this is like the first question. You have observations until a certain day, and they're asking you to find what is the weather at that particular day. We know how to compute this. Now if you look at this one, I scratched the purple part because if you remember, due to the assumption of output independence, if you have something like this, it will get reduced to this. So what is something like this? You have an observation. So what the probability of an observation given you have a sequence of hidden states and sequence of previous observations. So this will boil down to probability of the observation given only that current hidden state. It will not depend on all the other hidden states or all the other observations.
Chocolate
Where was I? Oh, here. So if you realize this is what is this trying to calculate? The probability of a sequence of observations, particularly O2 and O3, right? So they will not depend on previous observations, so we can strike it off. And you might be asking, why did I not strike S1? Because this observation is there, no? It will depend on either S2 or S3, and either of those could come from S1. So that is why I didn't strike S1 off. You can't remove it, but I can remove these easily because they're observations. They will not give rise to either S2 or S3, but S1 could give rise to S2 or S3. So until I get S2 or S3, I won't be removing this. It will be there. Now, what does this get simplified to? So you have sequence of observations that are relatively future observations, right? If you're talking about day 1, observation 2 and observation 3 are relatively futuristic. Like with respect to S1, they are future observations. And S1 is the state that we are talking about. Is it raining on that day or not? We want to find the probability. But we are currently at day 3. So this is like a previous state. That's why I wrote previous state. So now I'll be simplifying this. How do we simplify this? I've told you a trick before, right? While trying to find probability of a sequence of observations. That is by introducing a state. Here we have O2, O3. So I will try introducing S2. S1 is given. It's given that it's raining. So what would S2 be? What is the state of S2? Is it raining on S2? Is it raining on S2, or cloudy, rainy. We'll be looking at that. So there's summation here because we do not know what happened on S2. And now again I did some grouping. So this is like some A, B and C. And then you apply this rule again, probability rule. And then you break everything apart, you split everything. What do you get? This is nothing but your transition probability. And here I'm removing S1 equal to R because I got my S2 here, and this in this sequence of observations O2 depends on S2. I don't need S1 anymore, so I can remove S1 because that is essentially the assumption of output independence. If you have the probability of an observation given any sequence of states and sequence of observations, it will boil down to probability of the observation given that current state. So in this case, you could think of the current state as S2 because O2 depends on S2. And we know that observations O2 and O3 are independent of each other. Right? So probability of A comma B. So if A and B are independent, I can say probability of A comma B is nothing but probability of A and B. But if you remember, I said these states are conditionally independent. So I wrote it in small text, conditionally independent. So what I'm supposed to write is probability of A comma B given something is equal to probability of A given C, probability of B given C. So this is when A comma B are conditionally independent. So I'll be applying that rule here. We know that all the observations are conditionally independent given the current hidden state. So I'll be splitting this. So you can consider this as A, B and C. So you have A given C and B given C. This is directly the transition probability and this is directly the emission probability. Now all that remains is computing this part. Now if you realize this is nothing but a future observation. So if you're telling given S2 is equal to X, we have to find the probability that O3, the observation on day 3 is dry. So this is very similar to this problem now. You have future observation given some previous state. So you have to do a similar calculation of some sort to calculate this one. You don't have to worry if you're not getting this. I think there are some algorithms that would help you solve this. So this is one way of solving again, but I think there are better algorithms. We'll see. There are two algorithms that solve two kinds of problems. So when I come to that, you'll realize. I mean here there are three kinds of problems, no? Computing the probability of the present, computing the probability of the past, computing the probability of the future. There's one more problem. The computing, we'll see. When we come to that, we'll see. There are four kinds of problems. So if you realize here, if you try to break this open, you're getting smaller subproblems. So you can do some sort of dynamic programming of some sorts. So in order to compute this one, probability of a sequence of observations given a certain state. So if you realize this is at time k, but all the observations are after time k. So again, this is like this is relatively in future with respect to time k, very similar to this one, right? So we are trying to solve problems like this. How do you efficiently solve problems that look like this? Because these kind of problems will appear in this one, which will appear in this numerator, right? So which essentially solves this problem. Probability of finding some probability of an event occurring in the past. given a sequence of observations. So what you're supposed to do is, first you compute probability of the observation at time t. So time t is the current time. In this case, t is 3. In this case, t is 3. Find the probability of the observation at time t given the previous state, t minus 1. So I told you a trick, no? How do you solve this? You just introduce, what do you introduce? You introduce a hidden state, yes. So introduce the hidden state as st. So you'll get a summation there. I mean, it's all math at this point. Everything else is the same. So here also I will be splitting. You have A, B, C, probability of A given C, B given AC. This one, I'm using this one. And here again you have the the assumption of output independence. The output at the observation at time t will not depend on any other thing than the current state. So this is the observation at time t, so it will only depend on state t. It will not depend on any previous or future states. And if you realize this is just the transition probability, this is the emission probability. So after you computed this part, now you compute probability of the sequence of observations at time t and time t minus 1 given the state at st minus 2. So this is like a pattern. You follow this pattern, you'll realize where we are going, because once you simplify this, you'll realize you'll be using the probabilities that you previously computed. If you look at this, this is probability of OT given ST minus 1, and we're using the same thing here. So you have to keep expanding this. So you first compute this, then you compute this, then you compute probability of OT minus 1, and then OT minus 2 given ST minus 3, and then it goes on until finally you reach this part. You reach your original question, which is this one. Probability of OT minus 1, so on and so forth until OK plus 1. So K is a number that's less than T, because that is what is required. No, we are trying to talk about something that happened in the past. Did it rain in the past given all these observations? So this way, this is like a form of dynamic programming. Using this method, you will be able to calculate this one, which means you will be able to calculate this number, which means you'll eventually be able to calculate this number, and then you'll be able to tell what was the probability that it was raining 2 days ago. That was the numerator. The denominator, you have probability of a sequence of observations given another sequence of observations. So these are relatively, they belong to the future with respect to day 1. And these are observations until day 1. So I wrote them here. I don't think there is any more simplification. So now you might be wondering, these are observations, right? They will not depend on the previous observations. That is only true if you have the hidden state here. If you have the current hidden state, only then you can wipe all these off. Now that the current hidden state is not given, you cannot wipe it off. So that is how conditional independence works. So you can't wipe this off directly. So I simply applied the normal probability rules. So probability of A given B is nothing but probability of A and B divided by probability of A. So this is the denominator. And we've seen how to calculate probability of a sequence of observations, which I showed to you people over here. Probability of sequence of observations. Just introduce a new hidden state. Don't introduce it randomly. Start from the back. So if O2 is the latest observation, you introduce S2. It depends. So here, if you're only finding probability of sequence of observations, you can introduce S2 because here O2 is there. If O3 is there, introduce S3. Fine. So I told you how this sequence of hidden states and sequence of observation looks like a Bayes net, right? So there's a method called variable elimination that uses this concept that this looks like a Bayes net. So let's say you have probability of this one. You want to find the probability that S2 is R, probability that weather on day 2 was raining, and the observations are dry, wet, wet. So you can treat this like a Bayesian network. So you remember Bayesian network, no? You start from the opposite side of the arrow. So you go like this. I mean, you can go anyway, that is, it doesn't matter. So if you start from this side, so S naught, so probability of S naught, you can write, but before doing that, if you notice, in this all the information is not given. You only have S2, O0, O1 and O2. You have S2, O0, O1 and O2. You don't have S0 and S1. So if you want to introduce S0 and S1, you have to add summation, because S0 and S1 could have been anything. If S2 is R, S0 and S1 could have been anything. It would have been sunny, cloudy or rainy. So once you introduce S0 and S1, ensure that you put a summation. So that summation goes from S, C and R. So Y will once take sunny, or else it will once take cloudy, or else it will once take rainy. Same goes for X also. It is S, C or R. So now that you have this, now you can use your Bayesian network formula. No? Now you can split it simply. So probability of S0, you can write it because it has no dependencies. And when you write probability of S1, S1 is dependent on S0. So you write probability of S1 dependent on S0. So probability of S1 given S0. And when you're writing probability of S2, it is dependent on S1. So probability of S2 given S1. And we're writing for O0, you have to write O0 given S0. So you have O0 given S0. O1, so O1 dependent on S1, you have O1 given S1. O2 is dependent on S2, so you have probability of O2 given S2. So this will make sense if you have listened to yesterday's Bayesian networks class. And now that everything is neatly divided, maybe you could use this method to solve HMM. There's some theory on dynamic Bayesian networks which I didn't go through, but you could go through. I'll go through it later. Okay, these were the 4 kinds of questions I was talking about. Even in yesterday's class, there was some theory that popped up about inference tasks. So what we did was, in the first question, we had a sequence of observations, and we had to find until time t, and we had to find out what is the probability that so and so thing was happening at time t. The weather, in this case, the weather. So if you're inquiring about the probability of the current hidden state, then that is called filtering or monitoring. And if you're inquiring something about the future, it is prediction. If you're inquiring something about the past, it is smoothing. So how future? If k is greater than 0, it means you have observations until time t, but you're inquiring about the probability of something that would happen in the future. Now this is, and if your k is less than t, you're inquiring about something that happened in the past, even though you have observations until time t. So that is called smoothing. The fourth kind of question is what are the set or what is the set of hidden states that could have possibly given rise to these observations? There could be many sequence of hidden states that could have given rise to this specific sequence of observations, but the fourth question is more interested in which is that combination of hidden states that will give rise to the maximum probability. So that is the meaning of argmax. So which argument should I give to this function so that I get maximum value out of it? So in this I have to give hidden states in such a way that this probability is maximum. There is an algorithm that solves this. At the end of HMM we will see what that is. That is the Viterbi algorithm. There's one forward algorithm as well. I think that solves filtering, but we'll see. I don't remember, but I'll see. One of these problems it solves. For the other two problems, I think you might have to resort to the methods that we discussed previously. So filtering is essentially you have, see, by this I simply mean you have O0, O1, O2 until OT plus 1. If you got confused with the syntax. So filtering, probability of S. So let's say we are at time t plus 1 and we want to find the probability of hidden state t plus 1 given a sequence of observations until time t plus 1. I didn't do anything here. I simply separated OT plus 1 from the sequence of observations. And if I apply rules of probability, I'll get this one. And for this observation, I have a current hidden state. So by the assumption of output independence, I can strike this off. This will not depend on this. This observation will depend on the current hidden state. So this is a constant. So I'm just writing this 1 by denominator as alpha. We know how to calculate that number. And in the denominator, if you see what is there in the denominator, you have this one. This is an emission probability, right? Probability of an observation given a hidden state. This is emission probability. And now you have this one. Probability of a hidden state given a sequence of observations. So here again we did that same trick. You introduce one more hidden state and take summation of it. In this case I took ST. So ST plus 1 I took ST. So ST could be sunny, rainy or cloudy. And again I'll apply rules of probability. A, B, C. So A given C. So this is A, B, C. This is B given C. Then this would be A given B, C. Yes, it works. Now again, there is this Markov assumption that the probability of a hidden state will only depend on the previous hidden state. So it will not depend on anything else. So I can strike this observation off. So now this simply becomes your transition probability. And now if you look at this, it is similar to the original problem. All that changed is instead of t plus 1, you have t. So this is some form of a recursive relation. So if I say this is f0 to 1 plus t, I can write it as alpha times some algorithm. You can think of this as some computation. So some function called forward, which will depend on f0 to t. So if this is f0 to t plus 1, this is f0 to t. and you'll also have to provide the sequence of observations. Fine, this was just a recursive relation. Now we'll look at one question. This is one HMM. You have sequence of hidden states, you have sequence of observations, you have something similar to the transition probabilities matrix. You have your emission probabilities, and then you have the initial probability. So let's say someone's asking you to find what is the probability of R1. So again, R1 is a random variable, so you will get a vector of probabilities. So I told you a trick, no? If you have this, you introduce one more variable. So here I introduced R0. But R0 could have been anything. It could be raining or not raining. So you have to take a summation. Apply the rules of probability. I get this one. And now I will expand R1. If I have to write it in terms of vector of probabilities, R1 could be raining or not raining. Notice that it is in small letters now. So it's either raining or not raining. Now I can open the summation, I'll get this one. Now I just have to substitute values. So this is a transition probability. This probability is already given. This is an initial probability. Let's look at how I got the numbers. So probability that it will rain on, so probability that R1 given R0. R1 given R0 means R1 is R0 is true. R0 is true is given. So if R0 is true is given, then what is the probability that R1 given R0? So basically 0.7. So that's how I got 0.7 here. And probability of R0 true is given here. So this is true, this is false. This is R0, this is not R0. Or in other words, R0 is true, R0 is false. Let me take one random example. So let me take this one. How do I get this probability? Probability of R1 given not R0. Not R0 means this one. Let's say it will not rain on day 0. Then what is the probability that it will rain on day 1? That is 0.3. You have 0.3. Let's look at this one. Not R1, not R0. So given not R0. So it will not rain on day 0. That would mean this one. Then what will be the probability that it will not rain on R1 given not R0? So this is true probability. The false probability will be 1 minus 0.3, which is 0.7. So you have 0.7 here. So finally, after doing all the math, you get 0.55 here, 0.5, 0.5. One more question is there. Probability of R1 given U1. So small u1 means you had an umbrella on day 1. The observation was someone had an umbrella at day 1. So this will change the probability. How do you find this? Here we applied Bayes' rule. Probability of B given A is nothing but probability of A given B into probability of B divided by probability of A. This 1 by probability of A, I am simply writing it as alpha. Here in this case, it will be a normalizing constant because we'll be getting a vector of probabilities. And why will we be getting a vector of probabilities? Because we are dealing with a random variable. So if I open R1, R1 is either raining or not raining. So you have R1 raining, not R1 not raining. Now this is an emission probability. This probability we already computed. Here PR1 P not R1 is also here. So let's see, how do you get this number? Let's look at the table. How do you get this number? Not R1 is given. We have to find probability of U1 given not R1. Probability of U1 given not R1. So let's say not R1. So let's say not R1. So what is the probability that U1 given not R1 is there? It is 0.2. So you have 0.2. So you keep looking in the tables and you keep substituting the values. So after you solve this, we know that this is a vector of probabilities, no? So somehow by definition this alpha is supposed to be the normalizing constant. If you wish to find this 1 by probability of whatever, you can do that also. But then if you know that you have a vector of probabilities, alpha will always normalize this vector. So in this case, how do I find alpha? Alpha is nothing but 1 by 0.45 plus 0.10. If you go by the probability way also, you'll get the same value. But here you don't have to do all of that. You simply write alpha, and at the end when you get a vector, simply do 1 by summation of the elements of that vector. So finally you'll get the vector probability of R1 given U1. So this means probability that it rained on day 1 given someone carried an umbrella. Probability that it did not rain on day 1 given someone carried an umbrella. Let's look at one more question. Probability of R2 given U2 and U1. They are small u2, U1. It means someone carried an umbrella on day 1, someone carried an umbrella on day 2. What is the, given this piece of information, what is the probability that anything could happen on R2? So this is a random variable. Anything could happen. It could either rain or not rain. So we'll be finding both the probabilities. If someone gives a probability of R2 equal to true, or someone, instead of capital letter, if small letter was there, then we wouldn't have to find both the probabilities. We would just have to find one probability. Fine, now that they asked us this one, so let's calculate. I have sequence of observations U2, U1, no? So I would also, it would be better if I have R1 as well. So I will introduce R1. See, you cannot introduce R3 here. It would be pointless. I would like to know what happened up until that day, right? Until R2, what happened? If you have all that piece of all those pieces of information, you'll be able to solve this problem. So that is the reason why I'm introducing R1, not R3, R4 or whatever. And one more reason is that you've already computed probability distribution of R1. So if you try to break things down into what you've already computed, it will be much easier. Similar to dynamic programming. So after introducing R1, using the rules of probability, we again applied that rule, no? A given B, comma C, A given C. And by the assumption of this Markov assumption, the probability of a hidden state will only depend on its previous hidden state and not on anything else. So I can strike off the observations. And if you look at this probability, the probability of R1 will not depend on the observation at the other day, right? It makes no sense. So you can strike this off too. Wait, did I write this correctly? I'll check this once and I'll get back to you. But you get the idea, right? This is how you solve problems. Smoothing is inquiring into the past, no? So you have some mathematical mumbo jumbo here that somehow shows you how to write the recursive relation. This will make more sense to you if you understood what happened here. So they're trying to represent our problem in terms of a constant and two other functions. This forward message we've already seen in filtering. This one. This was the smoothing problem, no? If you realize, this is nothing but the filtering problem, but until time k. And this is nothing but the backward message. What is the backward message? If you have something like the probability of the relative future observations given the past hidden state that we are talking about, if you remember this, probability of relative future observations given a past state. So future means future of that previous state, not our future, but the future of the previous state. So probabilities of this form is the backward message. Probability of this form, probability of a certain state given observations until that day. So that is the forward message. And alpha is the other part, the 1 by denominator part. So what this problem is smoothing. In smoothing itself, you have the forward message, you have the backward message, you also have 1 by denominator, which is the alpha. So if you've understood that part, this part is nothing much. It is just a representation. So alpha is 1 by denominator, and then forward message, we saw it in filtering. It is until k only. In the original filtering problem, it's until it's from 0 to t, right? But in this smoothing problem, it is 0 to k. And then I think I don't have to spend much time here. This also we got from the derivation over there. And this is how we write the recursive relation. Fine, we'll solve one more problem. Let's see. Yes, so the algorithms are here. The algorithms have come to your rescue. This is one HMM problem. You have a set of states, you have set of observables, you have the transition probability matrix, emission probability matrix, and then you have the initial probability distribution. So how do you decode this piece of information? So you have rainy and sunny, no? So this is rainy and this is sunny. This is rainy, this is sunny. So if you're transitioning from rainy to rainy, it is this one. If you're transitioning from, let's say, sunny to rainy, this is rainy, sunny, no? So rainy, sunny, rainy, sunny. So sunny to rainy means sunny to rainy. So this 0.4. You have to first look at the row and then look at the column. So sunny to rainy. Sunny to rainy means this is rainy. Oh, I've already checked. What about rainy to sunny? Rainy, and then sunny. 0.3. If you look at emission matrix, this is rainy, this is sunny, this is walk, this is shop, this is screen. So rows will represent the hidden states and columns will represent the observables. and the probability that you'll get is, for example, this probability represents probability that the observation is sharp given the state is sunny. So basically, if you have Bij, I is the state, J is the observation. So these are the states, these are the observations. Anyways, question. So let's say you have this question. Probability that you observe this given sequence of observations. So we have an algorithm that helps us solve this problem. It's called forward algorithm. There is a procedure for forward algorithm. It is, see, these algorithm problems are simple if you know what the algorithm is. So this is the algorithm. So you have just 2 lines of computations that you're required to do, and if you keep performing this, you will get your answer. So this is okay, first I'll come to this and then I'll come to this first line. So alpha kj is nothing but the probability of the hidden state being the state j. So you have so many states here, no? You have state 0, state 1, state 2, state 3, and so on and so forth. So at time k, so here k is the time. So probability that at time k, the state is the jth element of the set of states, and along with that you have some set of observables until time k. So that probability is represented by alpha kj. So k is the time, j is the element, the index of the state in the state array, in this array, which state is it that we are talking about. So if j is 0, it is rainy. If j is 1, it is sunny. So now that you've understood what alpha kj is, I don't have to tell what alpha ki k minus 1 I is. It is nothing but probability that at time k minus 1, the state was the ith element of the set of states, and then you have all the observations until time k minus 1. And you know what Aij is. Aij is the transition probability. You're transitioning from state I to state j. So row I, column j, you have to find your probability from here. Bj ok. So Bj ok is the emission probability. Here j represents what is the state that you're currently at, and ok is the observation at time k. So if the observation is sharp, so sharp is the second observation, no? In the set of observables. Mind you, this is the set of observables, and this is the sequence of observations. Do not confuse them. The sequence of observations can change. You can find anything. You can find probability of sharp, walk, sharp. The length can also change. Can have a very long sequence. But this is the set of observables. Once you fix this, do not change the order. Let us keep it that way, because the probabilities in the transition matrix and the emission matrix, it depends on the order that you fix here. So if it is rainy, sunny, it means this is rainy, this is sunny, this is rainy, this is sunny, this is rainy, this is sunny. And if you fix the order that it is walk, shop, clean, so this has to be walk, shop, clean. If you change the order here, then the meaning changes here. So don't change this order. But this order depends on the question. What is the sequence of observables? So Bj, OK. So Bj, J is what state you currently are in. OK is the observation at time k. So observation at time k, don't come looking for the observation here. Observation will be given in the sequence. So at time k, time 0, time 1, time 2, what is the observation? Depending on that observation, you have to go here and look at the emission probability matrix. We'll look at an example. Okay, wait, the first line. So first line is for computing the initial alpha value. Here, this second line will work for k not equal to 0. If k is equal to 0, you're supposed to use this. It's the same as this, it's just that instead of this summation, you have the initial probability, which will be given like this. Initial probability distribution. If you remember the green color formula that we used for filtering, it is essentially the same thing. This is how we got this. You have the transition, you have dependence on the previous probability, and then you have the emission thing as well. So this algorithm is derived from probabilities only. So you can choose to either use this algorithm or choose to stick with probabilities. This problem is for finding the probability of a sequence of observations. Now we'll start using the algorithm. So first we'll have to compute alpha 0. So now it's just a matter of substituting values. So O0 is walk because it is given. O0 is walk. So how do you act? So pi 0, pi 0 is... Now it's just a matter of substitution. Just apply this for the first time and keep applying this until k reaches this value. So you have to do until k becomes 2. So you'll get alpha 0, alpha 1 and alpha 2 as well, and that's where you stop. Okay, fine. So how do you compute B0 walk? B0 walk means you go to the 0th row and go to the walk column. So 0th row, walk column. Where is walk column? This is walk, shop, clean. So walk column is here, so 0.1. 0.1. So you keep substituting values. So after you compute until alpha 2, and if you would ask me what are these J's and I's, I told you they're states, right? So in this question you have 2 states, so you only have zeros and ones. J will be zeros and ones. If you had more number of states, you would have had alpha 0, 0, alpha 0, 1, alpha 0, 2, and so on. Since you have only 2 states, you have only 2 calculations to be done. After you calculate until alpha 2, the answer to our question will be summation of the last 2 alpha values. If you have 3 states, then you'll have to add all those 3 numbers. So for the last iteration, whatever numbers you got, you have to add them, and that will give you the answer. So this is the forward algorithm, which is used to find the probability of a sequence of observations. The other question is the argmax question. What is the sequence of hidden states that will maximize the probability of the sequence of hidden states given a certain sequence of observations? Or in other words, what is that sequence of hidden states that most likely gave rise to this sequence of hidden states? We have the Viterbi algorithm to save our day. This is very similar to the forward algorithm. Instead of alpha, now you have delta, and instead of a summation, all that you're supposed to do is find the maximum. Everything else is the same, but here there's no summation, there's max. So apply this algorithm. So j is 0 and 1 because you have only two states, so you get 2 of each, and continue until time becomes 2. So k will be going from 0, 1 and 2. So you have 0, delta 0, delta 1 and delta 2. Now after you've computed delta 0, delta 1 and delta 2, we shall compare all the values. So in delta 0, which state is the highest? Like which state got the highest delta value? In this case, delta 0, 1, because this is greater than this, and so on and so forth. This is greater than this, and this is greater than this. So if 1 is greater, it means if you would have picked state sunny, you would get a higher probability. So the first state will be sunny. Here also sunny. And since the probability became maximum when you picked state rainy, 0 is rainy, 1 is sunny. How is 0 rainy and how is 1 sunny? It's because of this order. We fixed the order in the state of in the set of states. So 0 is rainy, 1 is sunny. So that's why don't change this order. Go along with the same order. So if 1 is greater, put sunny. If 0 is greater, put rainy. So that this is what you got. So this is that set of this is that sequence of hidden states that could have this is the sequence of hidden states that could most likely give rise to this sequence of observations. Like this will give the maximum probability. If you can take any other sequence of hidden states, any one of them could have given rise to this sequence of observations, but the maximum is given by this sequence of hidden states. So that is the end of HMM. And then comes knowledge representation. There's a lot of theory in knowledge representation, so you can go through the theory from pages 1 to 10 by yourself. Proposition. It's either true or false, so you can look at these examples. True, false, that's it. Predicate, it depends on the variable. So predicate looks something like this. You have a variable n here. So if I substitute n with 10, so now it becomes a proposition. It's either true or false. But this is a predicate. These two are propositions because it's either true or false. But this is neither true nor false. It depends on the variable. So following that, you have propositional logic and predicate logic. In propositional logic, you have logic. So what is logic? That is covered in the theory. So read these first 10 pages. What is logic? Logic is covered in the theory part. What is propositional logic? Logic that is described using propositions, connectives and brackets. Connectives are basically all those and, or, implies. So something that looks like this. This is propositional logic. You have some literals which are either true or false, and this entire thing is also either true or false. This is propositional logic. We have one more example. Today is wet. So it is a proposition. It's either true or false. John likes apples. True or false. So they're all propositions in this. Predicate logic is like, now you get it. No, you just use predicates. And since you're using predicates, you'll also need variables. And in addition to that, you also have quantifiers. For example, your predicates look like this, no? You have P, fen. So in P here is wet, and I've substituted a value. Instead of n, I kept today. So this is predicate logic. You're using a predicate and then you've substituted values also in that. If you notice, these two examples convey the same meaning, but this is a proposition. It's either true or false. The truthfulness of this can change depending on what is given as an input here. So this is a predicate. Predicate which has been substituted. And even these two, John likes apples. Likes John apples. We're using a predicate there. So atom is like the smallest unit of logic. If you look at propositional logic, the smallest unit are these literals that you can't break apart. And all those atoms in propositional logic are propositions. This is a proposition, this is a proposition. But in predicate logic, the atoms are predicates. You can't break this apart. So this part that you can't break in a predicate logic. The unbreakable part in a predicate logic is the predicate. You have some more examples, so you can write something like this. This is propositional logic. You have proposition, 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 and then you have connectives in between. But in predicate logic, you can use quantifiers like for all, and then there's this is universal quantifier. Existential qualifier is this one, quantifier, and then you can also use variables, and you can use predicates. So it makes it predicate logic. And in particular, this is an example of first order predicate logic. And you can informally call propositional logic as zeroth order propositional, zeroth order logic, first order logic, or specifically first order predicate logic, because you have quantifiers, variables, and all those things. How is it different from higher order logic? So for example, I talked about second order logic here. In first order logic, quantifiers only apply to variables, but in second order logic, they also apply to relations. So you have these quantifiers, right? For all, there exists. If you use it only for variables, then it is still first order logic. But if you use it for something like, let's say, for all f, if f of 0 is 0, then I can say red f. So in this case, I just wrote something that belongs to higher order logic because I'm applying a quantifier to a function. Function is not a variable. So this is an example. So if your quantifiers are restricted only to variables, then it's still first order logic, or else it increases. The order increases. So you have something called rules of inference. I don't seem to find these examples in the slides, but I remember them being discussed. So for example, modus ponens, modus tollens, all these syllogism and all those things. You can look at some examples. So for example, if it is known that money implies happiness, and it is also known that you have money, then you can declare that there is happiness. That is modus ponens. If P implies Q and P, if both of them are true, then Q is also true. So money implies happiness, and you have money, so you have happiness. Modus tollens, P implies Q and not Q, so it means not P. So money implies happiness, but you're saying you don't have happiness, it means you don't have money. And you have transitivity, P implies Q, Q implies R. So this is all simple, no? You can do all of this. I stopped writing examples because it is simple. You can write examples of your own. So P or Q, and it is also given not P, therefore Q. So what does it mean? It's like friendship or love, but you're also saying no love. It means you're saying yes to friendship. Because if you know this is true, and if you know not love is also true, so for this thing to remain true, friendship has to be true. So that is rules of inference for you. And then I think there's something called resolution theorem later. We'll see. Contradiction. Contradiction is like you have P, and then you want to prove P is true, but what you do is you start with not of P and keep making inferences. Finally, if you reach false, it would mean, what does it mean? It would mean that not P implies false. So finally, if you reach this place, this would imply that P has to be true. Why is this the case? Because if you look at the truth table of implication, something implies false. This statement can only be true if this something is false. And in this case, we are saying that not P implies false. So if not P implies false is true, then not P has to be false. And if not P has to be false, P has to be true, and that is why contradiction works. So proof by contradiction is you want to prove P, you start with P, you keep looking at what's going to happen, and if you reach a place where you have conflicting opinions, you say it's not true. If you don't reach any conflicting thing, you can say no. I don't think you can say it is true. I think contradiction is used to prove it's not true. Anyways, so if you reach this, you can say it is true. If you're unable to reach it, then you can say there is a contradiction and be like it is not true. There's an example for inference. So let's say these two sentences are given, statements are given. So this is in first order logic, right? I mean, this entire thing is FOPL, first order predicate logic. You're using variables, quantifiers, and predicates. So it is given for all x. What is the condition? Man x implies mortal x. This is given, and it is also given that Socrates is a man. Now what I can do is since statement 1 is true for all x, it would mean it is also true for Socrates, right? So I'll substitute Socrates in this. So if I substitute body like it, I'll get man Socrates implies mortal Socrates. See, they told for all x, so x can be anything. So instead of x, I kept Socrates. So I substituted Socrates in x of equation 1. Now that I have these two statements, I can use modus ponens. What is modus ponens? I have P implies Q, and I also have P. It would mean Q is true. That is modus ponens. So from I am applying modus ponens on 2 and 3, then I will get mortal Socrates. So this is how I can prove using first order predicate logic and rules of inference that Socrates is mortal given certain conditions. And then you have some theory. I couldn't collect examples for this, but you could try searching for some examples. I will try filling this document later if time permits. There's something called the resolution algorithm, which I remember uh, listening to when sir was trying to explain, trying at least. So resolution algorithm, you have some steps. Uh, you have to convert sentences to conjunctive normal form, so CNF, and there's something called DNF as well. That's a different thing. So first, let's look at what is conjunctive normal form. Conjunctive normal form is nothing but it's a conjunction of disjunctions of literals. So let's say you have literals A, B, C, D. These are literals. So disjunctions of literals means you just have statements where literals are separated by an or, and such statements you're joining with an and. So conjunction of disjunctions of literals. So this form is called conjunctive normal form. If you do the exact opposite, where you join the literals using and you will join such statements with an or, it becomes DNF, disjunctive normal form. I think you might want to look at examples where you will be able to convert statements like P implies Q to conjunctive normal form and other things. That will help us do the first step, convert sentences to conjunctive normal form. I think there's a video. I think I found a video. I will upload the link to AI stuff folder. It explains this conversion, and there are 2 more videos that I found. You could possibly watch those 2 videos. I'll provide the links to these 2 videos. There it discusses what is the resolution principle, and then it has some examples also. So it will give you the premise also. What is this resolution principle and what are we trying to do? Why are we doing all these things? So we're doing this because we want to prove something is true or not, given a set of statements. We will see if they're all consistent with one another. We would like to see if we could reach a solution at the very end, a simplification of some sorts. So you can watch these 2 videos. You don't have to worry when I said time's up. It's just that I didn't write anything more. So now I'll be screen sharing the slides. So I think I've covered until this part. See, look at this. This is resolution. This is resolution theorem, but I don't know. How do I turn this? So look at those 2 videos. So assuming you did look at those 2 videos, we'll be moving on. It's not, you don't have to watch it right away because it will not be popping up for the rest of the 40 odd slides. Conceptual graphs. So you can read the theory. Conceptual graphs are essentially this. You have concepts in rectangular boxes, and then you have relations between concepts in ovals. So this is one simple conceptual graph. This is a better example. So let's say you have a sentence. A monkey scratches its ear with a pawn. So in this sentence, monkey is a concept. Scratching is also a concept. Ear is also a concept. And pawn is also a paw. Okay, this is not pawn, but paw. Paw is also a concept. So you have 4 concepts. So you write monkey, scratch, ear and paw. Now let us think about scratching. Who is scratching? Monkey is scratching. So the agent of scratching is monkey. How is the scratching done? What is facilitating the scratching? The paw. Paw is facilitating the scratching. So uh, scratching paw is the instrument of scratching. So scratching is done through paw. So paw is the instrument of scratching. What is being scratched? What is the object of scratching? That is the ear. So you get my point, no? So you have concepts in between. Concepts are joined by relations. So you have agent, instrument, object. No, that was scratching. Scratching is done. Let's look at ear. This ear, whose ear is this? It belongs to the monkey. So ear is a part of monkey. And the same question goes to paw. Whose paw is this? It is the monkey. So paw is a part of monkey. It's not like there would be one correct answer to a conceptual graph, but if all of us sit together, sit down and then try drawing conceptual graphs, most of it will more or less be the same. So now that all of you have looked at this example, all of you will more or less try to draw conceptual graphs that look like this. So it's fine. Okay, now they're saying each concept has a type and an instance. So for example, uh, like I'll give an example of what is a type and an instance. So human can be a type, and an instance of that type is like, for example, an instance of a human being is Pranav. It's like, what is Pranav? It's like a kind, a specific instance of human. There are many instances of human beings on this planet. One being me, the other, the others being you all. And for one more example, a type could be tree, and an instance of that tree could be the tree that is behind the building that you are in currently. So you get my point. You have types, and then you have some instances of those types. So they're saying general concept is a concept with a wildcard instance. So if you look at this conceptual graph, you have brown and dog and color. So it's saying brown is the color of dog. So dog is a type here, and they gave star X. So I think they wanted to mean any instance X of type dog. So basically any dog. So you get the point, right? Instance and type. So this is a general concept. It applies to any dog. But if you look at specific concept, it's saying a concept with a concrete instance. So it applies to a certain very specific instance. So if you look at the second conceptual graph, you have dog Emma. So Emma is the instance, dog is the type, and this conceptual graph is only concerned about this specific instance, Emma, which is a dog. So they're basically talking about a dog called Emma specifically. If you're talking about all dogs, you can go for the first graph. Now hierarchy. Look at animal, look at dog, look at cat. Dog is an animal, cat is also an animal. So it's like animal is some sort of a super class. It's, or you could think of it, it's on the higher level of hierarchy. It's much more general. Dog and cat are specific kinds of animals, and within dogs and cats you can have multiple instances. You could think of dog and cat as instances of animals too, if you would like to think of it that way. Or you could say dog is a specialization of concept. If animal is a concept, dog is a specialization, a specialized form of animal. A cat is a special form of animal. That is what they're trying to say here. Canonic conceptual graph. So they're saying it is canonic if it is a sensible representation, but it need not be true. For example, black is the color of rice. See, this is a very sensible conceptual graph. You have concepts, you have relations. So this is a canonic conceptual graph, but the knowledge that it's trying to, the knowledge that it contains is false, because the color of rice, at least the rice that they clean, the and with all the anyways, the color of rice is not black, so the information presented is false. But this is a canonic conceptual graph because it is a very sensible representation of knowledge. These, okay, you have some four rules here: copy, restriction, join, simplification. There are some examples related to this within the same PPT. So instead of going through this text, I will show you the examples. So copy, restriction, join, and simplification. Restriction of concepts. So restriction of concept, what is restriction? Substituting a concept in a graph with its specialization. So if you look at the first, there are four conceptual graphs in this slide in front of you. Look at the first conceptual graph. You have eat. Eat is performed by a person. So person is the agent of eating. And what is being eaten? Pie. So pie is the object of eating. Look at the arrows on the right side. So specialization of this. So the second graph is a restricted form of the first graph. And how is it restricted? You replaced person with a girl. Girl is a specialized form of person. So that is how the second graph is a restricted form of the first graph. If you look at the first one and the third one, here they've replaced person with person Sue. So this is a specialized form. So how is it specialized? Here we are literally replacing person with a person who's called Sue. So this is very specific. You've literally replaced a concept with you replace a type with an instance. So this is very, very specific. If you look at 1 and 4, they replaced person with a girl, which is a special form of a person. And not only that, they also wrote Sue. So they're talking about a girl named Sue. So from a person, we came to a specialized form girl, and then within girls, whoever is named Sue. So you get restriction, right? You just have to replace a concept with a specialized form of the concept. Joining. Joining is, look at the first two graphs. The same person, see, the concepts are repeating here. Girl, Sue, and eat and agent is the relation. These three are repeating. The other two are not repeating. So what we can do is we can join the first two graphs and make one single graph. So eat is being done by a person. I mean, you could have retained girls you, but it doesn't matter. Here we are focused on how to join two graphs. So eat is being done by a person, and the object of eating is pie. The manner in which you're eating is fast. So joining, you're just joining here. Simplification. So if you look at the first graph, it makes no sense to have two agent nodes. Eat is performed by just one agent, right? If you have multiple agents, you need multiple people. But here it's just one person that's eating. So you can simplify by removing unnecessary nodes. So you remove one agent and then you have your final conceptual graph. So this was inference rules. Canonic formation rules. Nice. So restriction, joining, simplification. So we saw what first order predicate logic is, right? So you can apparently convert first order predicate logic to conceptual graphs. You look at the example. So you have a first order predicate logic, right? There exists X such that Emma is a dog and Emma's color is X and X is brown. So I think X is some sort of a color. So there exists a color. They didn't say color, so I'm just saying X. So there exists X such that Emma is a dog and color of Emma is X and that X is brown. So if you get the idea, what is the idea here? Emma is a dog. So there's a dog called Emma and it is brown. So Emma the dog is brown. So how do you represent this using conceptual graph? So you write down the concepts. You have dog Emma, you have brown, and both of them are related through color. Brown is the color of dog Emma. So you can simply draw this uh, conceptual graph. So they're saying every predicate becomes a node. In this, predicates are brown and dog. Color is also, see, node is of two types, right? It is either concept or relation. So here dog is a kind of a concept, so it became a concept. Color is a kind of a relation, so it became a relation. Brown is again a kind of a concept, so it became a concept. General concept, variable, specific concept, at in this case I didn't have to write anything with respect to X. Maybe something similar to this. You have X here, it's a general concept, maybe something of that sort. I mean, it goes vice versa too. So if you have a conceptual graph, I think you can convert it into first order predicate logic, is what I'm thinking probably. I don't know what am I supposed to say here. But anyways, we've seen all of this. You'll have to know how to write FOPL. You'll have to know English to FOPL and FOPL to English. Some examples are given in a certain PDF. You could go through them. There is nothing that I could say. Let's just look at one example. Every rose has a thorn. Every rose has a thorn. So every rose. So if you're saying every, so there will be some form of for all quantifier. So I wrote for all X. And we're saying every rose. And when we say for all X, and when we say every rose, that X should be the rose, no? So X is rose. So we're saying for all roses. Now for all roses, what about for all roses? For all roses, what is there? We have thorns. So it has a thorn. So if X is a rose, it means, now again, they're using a quantifier and a variable. There exists something called Y. What is that something? That something is a thorn. So there exists a thorn and they're saying X has Y. We know X is a rose. So X has thorn. So for all roses, there exists a thorn such that the rose X has the thorn Y. So that is how FOPL is written. That is how it's written. That is how this FOPL has been written. So for all X, if X is a rose, then there exists Y such that X has Y and Y is a thorn. It looks like a very elaborate way of saying something very simple, but that's how it is. On Mondays and Wednesdays, I go to John's house for dinner. See, there are multiple ways to write FOPL. It's not like there is one correct answer. So if you're practicing FOPL, and if you think your answer is different from what is given in the slides, you don't have to worry, but then check. I think you will be able to check for yourself if the answer that you got is correct or not. On Mondays and Wednesdays, I go to John's house for dinner. Okay, they wrote for all X. Is Monday X? So X is some form of a day. So we are checking if the day is Monday or Wednesday. So if it is Monday or if it is Wednesday, then it implies that I will go to John's house for dinner, no? So for dinner, eat meal, or you could say eat dinner or whatever. So I will be going. So they wrote me, house of John, and X is a day. So you can get as creative as you want. You can create your own predicates. Here they've created their own predicates, and they're using all kinds of things here. Okay, if you notice, it says on Mondays and Wednesdays I go to John's house for dinner. But if you look at the predicate logic, we're using the connective or. But logically, that's how it is. If it is either Monday or if it is Wednesday, then only I'll go, or else I won't go to John's house for dinner. So this example showcases how English and FOPL need not always use the same connectors. Higher order, yes. So I told you in first order logic, the quantifiers will only apply to variables, but then in higher order logics, they can apply to functions as well, and predicates and more. So I think I gave a similar example, no? For all functions, uh, f is red implies f of 0 is 17, and f of 0 equal to 17 implies f is red. So function is red if it has a 0 at 17, or no, if it has 17 at input 0, and vice versa. So I think you can read all these theories, theory. I think after this we have something called, we will first go through semantic networks, I think, and then we'll go through production rules. Conceptual graphs we already went through. Frames, they have their own representation, so we'll look at that. Okay, first we're going through production rules. Okay, fine. Look at some examples. So the syntax is like this. You have if condition, then action. So if at bus stop and bus arrives, then action is get on the bus. So these are some examples of production rules. If condition, then action. Okay, so after what was this? Production rules. Graphs, we've seen conceptual graphs. They are some form of graphical representation. Semantics, I think the definition of semantics was covered in the first 10 pages of the lecture. You can see there what is semantics, what is logic, probably. Again, conceptual graphs have come. Frame. So frame is the new thing here. after conceptual graphs, you have frames. If you look at an example, you'll understand. So you have a concept lecture, and then you are providing details about the lecture, some properties or anything, any extra pieces of information. So it's called frames because you have a big box here. This entire frame is for lecture, and then within lecture you keep subdividing it into smaller frames. And what you can do is, within the frame you can add more frames. So this frame itself is another frame, and each of them can be different frames. So you can have a frame for Professor Jones, you can have a frame for operating systems, so on and so forth. So this is just like a different way of representing information. Frames. Okay, I have some examples. Okay, so you have some predicate logic here. In the next slide, what they do is they take all these statements and then put it in one semantic net. Semantic net is very similar to conceptual graphs, right? So you have concepts and relations. So if you let's pick something. For all x, human x implies living x. So I think you can build everything one by one. You don't have to get overwhelmed or something. So let's start with human. So human is a living thing, but human is a specialization of no, man is a specialization of human. So man is a human, woman is a human. John is a man. John is an instance of man. So you have instance, you have is a human has 2 legs, and an animal has skin and can move. Giraffe is, it's like a property now. Human having 2 legs is a property. So I think in a semantic net you only have properties, you have is a, and then you have an instance, mostly, I guess. Okay, frame network is basically a network of frames. No, I've not been speaking, so it's fine. I don't remember any of this being covered in class, so I don't think any of this would come. Inheritance, I think you people would know probably. It's like, let's say, human beings. The property of a human being is one of the properties of a human being is having two legs. So if you're an instance of the human being, you will automatically inherit all the properties of human being. So since you're a human being, you also have two legs. Or yes, there's nothing in this. So I think I will end for now and cover planning later. Fine. There's one more PDF that shows examples of FOPL. I think FOPL is very easy. There's nothing much. Once go through the videos of resolution, because I think resolution was discussed in class, and I don't think the notes are proper for that. So I'll end the meeting now. Good night.